There is an exact moment, precise and mathematical, when neutrons simply surrender. Not gradually, not over time, but in a single instant when the fundamental forces of nature reach a breaking point and matter itself admits defeat. Tonight, we'll find that moment together, that razor-thin line where quantum mechanics meets gravity in the most violent collision physics allows. We'll trace the journey of neutrons as they're crushed beyond recognition, compressed into densities so extreme that spacetime begins to curve inward, folding reality into a point of no return. There exists a threshold calculated and confirmed where the strongest force in the atomic nucleus finally whispers, "Enough," and the universe creates something it can never take back. And if this quiet exploration into the deepest mysteries brings you even a moment of peace, a gentle tap on subscribe means more to me than you might imagine. It helps keep these cosmic stories softly alive among the infinite darkness. Now, let's begin our journey to that exact moment. Part 1. Deep beneath the crushing gravity of a neutron star lies one of nature's most elegant prisons. Quantum mechanical force so fundamental that it alone prevents these stellar corpses from vanishing into nothingness. Tonight we explore the invisible barrier that holds reality together in the densest objects known to exist, a force born not from heat or motion, but from the very architecture of quantum mechanics itself. This force has a name, neutron degeneracy pressure, and understanding it means understanding why neutron stars exist at all, rather than simply collapsing into black holes the moment they form. To grasp this quantum prison, we must first journey into the strange world where matter behaves according to rules that seem to defy common sense, where particles refuse to be squeezed beyond certain limits not because they are hard like billiard balls, but because the universe itself forbids two identical particles from occupying the same quantum state. The Pauli exclusion principle, discovered by Wolfgang Pauli in 1925, stands as one of the most counterintuitive yet fundamental laws of physics, stating that no two fermions such as neutrons can share identical quantum properties within the same system. This principle creates what physicists call degeneracy pressure, a resistance to compression that exists even at absolute zero temperature, where all thermal motion has ceased. Unlike the pressure in a balloon, which comes from fast-moving gas molecules bouncing against the walls, degeneracy pressure emerges from quantum mechanics' pure mathematics, requiring no heat or motion to generate its push against gravitational collapse. Imagine trying to pack an infinite number of people into an apartment building, where the fundamental law of the universe states that no two people can live in exactly the same apartment, forcing newcomers into higher and higher floors as the lower ones fill up, with each floor requiring more energy to reach than the last. In a neutron star, this apartment building analogy becomes reality as neutrons are compressed into a space so small that quantum effects dominate the behavior of matter on a macroscopic scale. The numbers describing neutron star density stretch human comprehension beyond its limits, with matter compressed to roughly 10 to the 18th power kilograms per cubic meter, meaning a single teaspoon of neutron star material would weigh approximately 1 billion tons, equivalent to the mass of Mount Everest, concentrated into a volume smaller than a sugar cube. At these impossible densities, neutrons exist in a state of matter that has no equivalent anywhere on Earth, forced into quantum states so energetic that they move at significant fractions of the speed of light despite the star being cold by stellar standards. The pressure generated by this quantum resistance becomes enormous, reaching values that dwarf anything we can create in laboratories, yet it emerges not from any force we can touch or feel, but from the mathematical structure of quantum mechanics itself. This degeneracy pressure creates an outward push that balances the inward pull of gravity in a delicate equilibrium, allowing neutron stars to maintain their structure for billions of years without any fuel source or energy input. NASA's Neutron Star Interior Composition Explorer mission currently studies these objects by detecting X-rays from hotspots on their surfaces, attempting to map their structure and determine exactly how this quantum pressure behaves under the most extreme conditions in the universe. The temperature at these hotspots can reach millions of degrees Kelvin, yet even this intense heat contributes almost nothing to the pressure supporting the star against collapse, as the quantum mechanical effects dominate completely over thermal effects. Scientists working with the mission face the challenge of understanding matter in a state that cannot be replicated on Earth, where the very atoms that make up ordinary matter have been crushed beyond recognition into a sea of neutrons existing in quantum states that push the boundaries of our physical theories. Each neutron in this cosmic prison occupies its own unique quantum state, vibrating with energies that would destroy any known material. Yet somehow the collective behavior of these particles creates the stable objects we observe spinning in space with clockwork precision. The European Space Agency's upcoming missions will attempt to measure neutron star masses and radii with unprecedented accuracy, hoping to understand the exact relationship between the quantum pressure and the gravitational forces that shape these objects. As we drift deeper into this exploration tonight, we begin to see that neutron stars represent more than astronomical curiosities. They are laboratories where the fundamental laws of physics play out on scales both impossibly large and impossibly small, where quantum mechanics written in equations by human minds manifests as cosmic phenomena visible across billions of light years. The mathematical foundation underlying neutron degeneracy pressure reveals itself through an elegant equation that describes how quantum resistance scales with density, written as pressure proportional to density raised to the 5/3 power in the non-relativistic regime, a relationship that emerges directly from the quantum mechanical properties of fermions confined to increasingly smaller volumes. This mathematical relationship tells us something profound about the universe, that as we compress neutrons into tighter and tighter spaces, the pressure pushing back grows much faster than we might expect from everyday experience, increasing more rapidly than the simple linear relationship we see in ordinary gases. To understand why this particular mathematical form emerges, physicists invoke the concept of Fermi energy, named after Enrico Fermi, which represents the energy level below which all quantum states are completely filled at absolute zero temperature, creating a sharp boundary in energy space that determines how particles behave under extreme compression. Picture the Fermi energy as the surface of a deep ocean, where every quantum state below this level is occupied by exactly one neutron, while all states above remain empty. And as we compress the system, this Fermi sea deepens, forcing neutrons into higher and higher energy states that resist compression with increasing vigor. The mathematical beauty of this relationship lies in how it connects the microscopic quantum world to macroscopic stellar phenomena, showing that the same principles governing electrons in metals on Earth also determine the fate of objects containing more mass than our Sun compressed into spaces smaller than cities. When neutrons are forced into smaller volumes, the uncertainty principle demands that their momentum, and hence their kinetic energy, must increase, and since pressure represents the rate at which energy changes with volume, we arrive at this specific 5/3 power law that has no analogue in classical physics. For a time, this quantum pressure increases faster than the gravitational pressure trying to compress the star, creating a stable balance where the neutron star can resist collapse indefinitely, spinning quietly in space as one of the most precise natural clocks in the universe. However, Einstein's special theory of relativity introduces complications that become crucial at the extreme densities found in neutron star cores, where the mass-energy equivalence expressed in the famous equation E equals mc squared means that the very energy stored in the quantum motion of neutrons contributes to the gravitational field trying to compress the star. This creates a feedback loop where higher compression leads to higher quantum energies, which in turn contribute more mass energy to the gravitational field, requiring even higher pressures to maintain equilibrium, and at some point this process becomes self-defeating. The mathematical relationship changes fundamentally when neutron velocities approach the speed of light, shifting from the 5/3 power to a 4/3 power law for the relativistic case, and this seemingly small change in the exponent represents the difference between stable equilibrium and inevitable collapse. Recent calculations by researchers at institutions like the California Institute of Technology and Princeton University show that this transition occurs when neutron star masses approach approximately 2 to 3 solar masses, depending on the exact properties of matter, at nuclear densities that remain uncertain despite decades of experimental and theoretical investigation. The mathematics reveals a harsh truth about the universe, that quantum mechanical resistance, no matter how exotic or powerful, has fundamental limits that cannot be exceeded, and beyond these limits, nothing in physics can prevent gravitational collapse to a black hole. Modern astrophysicists working with data from gravitational wave detectors have begun to probe these mathematical limits directly, using observations of neutron star mergers to constrain the equation of state describing how pressure relates to density at the most extreme conditions accessible to scientific investigation. The laser interferometer, Gravitational Wave Observatory and its European counterpart Virgo have detected the signals from neutron stars spiraling into each other, providing the first direct measurements of how these quantum pressure laws behave when pushed to their absolute limits. Each detection refines our understanding of where exactly the mathematical ceiling lies, that point beyond which the elegant quantum resistance that has held neutron stars together for billions of years finally surrenders to the relentless pull of gravity. As we continue our journey tonight through the physics of stellar collapse, we carry with us this mathematical wisdom that the universe operates according to precise relationships that can be written in equations. Yet these same equations predict their own breakdown, the moment when mathematics itself points toward the unknowable. In the spring of 1939, as the world stood on the brink of global conflict, two physicists working at the University of California, Berkeley, were quietly solving equations that would reveal one of the most fundamental boundaries in the cosmos. J. Robert Oppenheimer, who would later become famous for his role in the Manhattan Project, collaborated with George Volkoff to extend earlier work by Richard Tolman on the structure of relativistic stars, creating what we now call the Tolman-Oppenheimer-Volkoff limit, a mathematical threshold that separates neutron stars from black holes with the precision of a cosmic guillotine. Their original calculation, based on treating neutrons as a simple degenerate Fermi gas with no interactions beyond the Pauli exclusion principle, yielded a maximum mass of approximately 0.7 solar masses, a result that seemed reasonable at the time but would prove to be a dramatic underestimate due to the simplified assumptions they were forced to make about the behavior of matter under conditions that had never existed in any laboratory. The calculation required solving the Einstein field equations for a spherically symmetric static distribution of matter, balancing the inward pull of gravity against the outward push of degeneracy pressure in a mathematical dance that becomes increasingly complex as relativistic effects begin to dominate. What Oppenheimer and Volkoff discovered was that unlike the situation with white dwarf stars, where electron degeneracy pressure can provide stable support below the Chandrasekhar limit, neutron degeneracy pressure faces a more fundamental constraint arising from general relativity itself, where the energy density contributing to the gravitational field grows without bound as the compression increases. Their pioneering work established that no static configuration of neutrons could exceed a certain critical mass, beyond which no force known to physics could prevent gravitational collapse to a black hole, making this limit as fundamental to stellar evolution as the speed of light is to motion through space. For decades after their original calculation, astronomers found no neutron stars approaching this theoretical limit, leading some to wonder if the boundary might lie much lower than their estimate, until observations of increasingly massive neutron stars began to push against theoretical expectations. The discovery of pulsars in 1967 by Jocelyn Bell Burnell provided the first direct evidence for neutron stars, but measuring their masses proved extraordinarily difficult, requiring binary systems where orbital dynamics could reveal the gravitational influence of these compact objects. As observational techniques improved through the late 20th and early 21st centuries, astronomers began finding neutron stars with masses approaching and exceeding twice that of the Sun, forcing theorists to recalculate the Tolman-Oppenheimer-Volkoff limit using more sophisticated models of nuclear matter at extreme densities. The challenge lies in understanding the equation of state for matter at densities exceeding those found in atomic nuclei, where neutrons may break down into their constituent quarks or form exotic particles like hyperons that exist nowhere else in the universe. Modern estimates of the limit, informed by gravitational wave observations from events like GW 170817, now place the boundary between 2.1 and 2.9 solar masses, a range that reflects our continued uncertainty about the fundamental properties of matter under the most extreme conditions accessible to scientific investigation. The August 2017 detection of gravitational waves from merging neutron stars provided unprecedented insight into this limit, as the rapid chirp of the signal suddenly cut off at the moment when the combined mass exceeded the maximum that neutron degeneracy pressure could support, marking the birth of a new black hole in real time. NASA's Neutron Star Interior Composition Explorer mission continues to refine our understanding by measuring the masses and radii of neutron stars with increasing precision, each measurement providing another data point to constrain the nuclear equation of state that determines exactly where this cosmic boundary lies. The European Space Agency's future missions will push these measurements to even greater accuracy, hoping to pin down the limit to within a few percent and resolve long-standing questions about the behavior of matter in regimes that stretch our physical theories to their breaking points. What makes the Tolman-Oppenheimer-Volkoff limit so profound is not just its role in determining stellar fates, but its representation of a fundamental boundary in nature where quantum mechanics and general relativity meet in a final confrontation that quantum mechanics cannot win. Unlike other limits in physics that depend on external conditions or specific circumstances, this boundary emerges from the deepest principles of space-time and matter, making it as inevitable as mathematics itself, a line drawn by the universe beyond which even the most exotic quantum forces must surrender to gravity's relentless pull toward infinite density and zero volume. At the heart of neutron star physics lies a profound paradox that emerges when quantum mechanics encounters the full power of Einstein's general theory of relativity, a confrontation that reveals why even the most exotic quantum forces must eventually surrender to gravity's inexorable pull. The crisis begins subtly, hidden within mathematical corrections that seem insignificant at first, but grow to dominate the physics as neutron star masses approach their ultimate limits, transforming the very pressure that once provided salvation into a contributor to the gravitational field demanding even stronger resistance. In the comfortable realm of ordinary physics, pressure represents a purely beneficial force that pushes outward against compression, like air in a balloon or water behind a dam, providing support without contributing to the weight of the system itself. However, Einstein's revolutionary insight that mass and energy are equivalent through the relationship E equals mc squared means that in the extreme environment of a neutron star, the enormous kinetic energies of neutrons moving at significant fractions of the speed of light contribute directly to the gravitational field trying to compress the star. This creates a feedback loop of devastating elegance where higher compression forces neutrons into higher energy quantum states, increasing the degeneracy pressure but simultaneously increasing the energy density that curves spacetime more severely, demanding even higher pressures to maintain equilibrium in a cycle that becomes increasingly difficult to sustain. The mathematical description of this crisis appears in the general relativistic corrections to the pressure equations, where terms that were negligible in Newtonian physics now multiply the pressure by factors that grow without bound as the neutron velocities approach the speed of light. Physicists working at institutions like the California Institute of Technology and Princeton University have spent decades calculating these corrections, showing that the simple relationship between pressure and density that works so well for ordinary matter breaks down catastrophically when relativistic effects can no longer be ignored. The Tolman-Oppenheimer-Volkoff equation, derived from Einstein's field equations for a spherically symmetric distribution of matter, reveals that pressure itself becomes a source of gravitational field, creating additional curvature in spacetime that pulls inward with the same relentless determination as the mass of the neutrons themselves. As neutron star masses approach the critical threshold, this relativistic crisis accelerates dramatically, with each increment of additional mass requiring exponentially more pressure to maintain stability, until the system reaches a point where no amount of quantum resistance can balance the gravitational collapse. The speed of light emerges as the ultimate speed limit not just for motion through space, but for the velocities of particles providing degeneracy pressure, and when neutrons approach this cosmic speed limit, the very physics that once protected the star from collapse becomes part of the problem rather than the solution. Recent calculations using the most sophisticated equations of state for nuclear matter show that this transition occurs with mathematical inevitability once neutron star masses exceed approximately 2.5 solar masses, though the exact value depends on nuclear physics that remains uncertain at the extreme densities found in stellar cores. The European Space Agency's gravitational wave detectors have begun to probe this regime directly, measuring the final moments of neutron star mergers where the combined mass crosses this critical threshold and quantum mechanics admits defeat to general relativity. Each detection provides new data about how matter behaves in this transition regime, where the familiar quantum mechanical description of particles in boxes gives way to a relativistic reality where energy and mass become indistinguishable and pressure transforms from salvation to doom. The mathematical beauty of this crisis lies in its inevitability, emerging not from any failure of human understanding, but from the fundamental structure of space-time itself, showing that the universe contains hard limits that cannot be overcome through cleverness or technology, but represent absolute boundaries written into the fabric of reality. NASA's theoretical astrophysics programs continue to refine our understanding of this relativistic crisis, using supercomputer simulations to model the exact moment when quantum pressure fails and the gravitational collapse begins, capturing in mathematical detail the transition from a stable neutron star to a forming black hole. As we journey deeper into this cosmic drama tonight, we witness the universe's most fundamental forces locked in a battle where victory belongs not to the strongest but to the most relentless, where Einstein's insights about the nature of spacetime ultimately triumph over the quantum mechanical principles that govern the world of atoms and molecules. Deep within the core of a neutron star approaching its maximum mass, there exists a critical density where the comfortable assumptions of non-relativistic quantum mechanics finally break down and give way to a regime where Einstein's special relativity begins to dominate the behavior of individual neutrons, marking the beginning of the end for the star's ability to resist gravitational collapse. This transition occurs not gradually, but at a specific threshold density of approximately 10 to the 15th grams per cubic centimeter, roughly 5 times the density of an atomic nucleus, where neutrons confined to increasingly smaller quantum volumes must move at velocities that approach significant fractions of the speed of light. At this critical point, the mathematical relationship describing degeneracy pressure undergoes a fundamental transformation from the non-relativistic form, where pressure scales as density to the 5/3 power, to the relativistic regime where pressure follows density to the 4/3 power, a seemingly small change in exponent that represents the difference between stable equilibrium and inevitable collapse. The physical meaning behind this mathematical transition becomes clear when we consider that as neutrons are compressed into smaller and smaller volumes, the uncertainty principle demands that their momenta, and hence their velocities, must increase proportionally, and when these velocities approach the speed of light, we can no longer use the classical relationship between momentum and kinetic energy that underlies non-relativistic quantum mechanics. Modern calculations performed at research centres like the European Organisation for Nuclear Research and the Massachusetts Institute of Technology show that neutrons in the cores of the most massive neutron stars move at velocities exceeding half the speed of light, creating conditions where special relativistic effects become as important as quantum mechanical ones in determining the pressure that supports the star against collapse. The mathematical singularity that emerges at this transition point represents more than just a computational challenge. It signals the breakdown of our physical description of matter under conditions that push the boundaries of both quantum mechanics and relativity simultaneously. As neutron velocities approach the speed of light, the energy required to accelerate them further grows without bound according to Einstein's relativistic energy formula. Yet the pressure these neutrons can provide begins to plateau, creating an impossible situation where infinite energy would be required to generate the pressure needed to resist further compression. Researchers working with NASA's theoretical astrophysics programs have shown through detailed computer simulations that this relativistic crisis develops over a timescale measured in microseconds once a neutron star's core density crosses the critical threshold, making the transition from stable equilibrium to inevitable collapse essentially instantaneous by astronomical standards. The point of no return manifests itself mathematically as a divergence in the equations of state describing neutron matter, where the relationship between pressure and density becomes undefined, and the differential equations governing stellar structure lose their physical solutions. The European Space Agency's Euclid mission and similar observational programs aim to detect the signatures of neutron stars operating near this critical regime, where quantum mechanics and special relativity engage in their final battle before general relativity takes control and mandates the formation of a black hole. Theoretical physicists have identified this transition as one of the most dramatic phase changes in the universe, comparable to the moment when a white dwarf exceeds the Chandrasekhar limit, but occurring at energy densities that exceed anything achievable in terrestrial laboratories by factors of billions or trillions. The mathematical elegance of this transition lies in how it connects three of the most fundamental theories in physics: quantum mechanics, special relativity, and general relativity, showing that nature contains built-in boundaries where one theoretical framework must hand control to another in a cosmic changing of the guard. Advanced gravitational wave detectors like LIGO and Virgo have begun to observe the final moments before this point of no return, detecting the characteristic frequency evolution as neutron star cores approach the critical density where relativistic effects overwhelm quantum resistance. Each such detection provides invaluable data about the exact location of this transition point, helping astronomers understand not just when neutron stars collapse, but why the universe contains such sharp boundaries between different types of physical objects. As we drift deeper into this exploration of cosmic limits tonight, we approach the moment where mathematics itself points toward the inevitable, where equations that once described stable matter configurations suddenly predict their own destruction, creating singularities that mark the end of one type of physics and the beginning of something far more mysterious and profound. Beyond the familiar realm of neutrons and protons lies a frontier of physics where the fundamental particles that make up ordinary matter may themselves break apart under pressures so extreme that they push us beyond the standard model of particle physics into territories where our most sophisticated theories begin to falter, and speculation must guide us toward possibilities we have never directly observed. At densities approaching 10 times that of atomic nuclei, the neutrons that comprise neutron stars may undergo a phase transition as dramatic as the melting of ice into water, but instead of molecules changing their arrangement, the quarks that make up each neutron may break free from their nuclear prison and form new states of matter that exist nowhere else in the present universe. This process of quark deconfinement represents one of the most exotic possibilities in modern physics, where the strong nuclear force that normally binds quarks together inside protons and neutrons finally loses its grip under the relentless compression of neutron star cores, allowing these fundamental particles to move freely through volumes much larger than individual nucleons. Theoretical calculations performed at institutions like CERN and Fermilab suggest that this transition might create what physicists call strange matter, a state where up and down quarks that make up ordinary matter are joined by strange quarks to form a soup of particles that could be even more stable than normal atomic nuclei. The mathematics describing this transition involves quantum chromodynamics, the theory governing the strong force, but the calculations become so complex at these extreme densities that even our most powerful supercomputers can only provide rough approximations of what might actually occur inside neutron star cores. Another possibility that emerges in this ultra-dense regime is the formation of hyperons, exotic particles containing strange quarks that exist only fleetingly in high-energy particle accelerators on Earth, but might comprise significant fractions of neutron star cores if the density and pressure become sufficient to make their creation energetically favourable. The European Organisation for Nuclear Research has spent decades studying these particles in terrestrial experiments, but the conditions inside neutron stars dwarf anything achievable in human laboratories, creating environments where particles might behave in ways that our current theories cannot accurately predict. The challenge for theoretical physics lies in constructing the equation of state that describes exactly how pressure relates to density in these extreme regimes, a relationship that determines whether neutron stars can exist at all above certain masses and what happens during the final moments before gravitational collapse to a black hole. NASA's theoretical astrophysics programs work continuously to refine these equations of state using data from particle accelerators, astronomical observations, and sophisticated computer simulations that attempt to model matter under conditions that existed only in the first microseconds after the Big Bang. The uncertainty in our understanding of ultra-dense matter means that we cannot calculate the exact moment when neutron degeneracy pressure fails and gravitational collapse begins, as this transition depends critically on physics that lies beyond our current experimental reach and may require entirely new theoretical frameworks to describe accurately. Some theoretical models suggest that strange matter might actually be more stable than ordinary nuclear matter, raising the possibility that neutron stars could undergo a rapid conversion to strange stars with completely different properties and potentially even higher maximum masses than conventional neutron star theory predicts. Other calculations propose that the phase transition to quark matter might occur gradually within neutron star cores, creating hybrid objects with conventional neutron matter in their outer layers and exotic quark matter in their centers, fundamentally altering the relationship between mass and radius that determines stellar stability. The Large Hadron Collider and similar facilities continue to probe the properties of matter at extreme temperatures and densities, but the conditions inside neutron stars combine both extreme density and relatively low temperature in ways that cannot be replicated in any conceivable terrestrial experiment. Advanced gravitational wave detectors offer our best hope for probing these exotic states of matter directly by measuring the detailed waveforms produced during neutron star mergers where the equation of state governing ultra-dense matter leaves distinctive signatures in the gravitational radiation emitted during the final moments before black hole formation. Each detection refines our understanding of what types of matter can exist under these extreme conditions, and helps constrain theoretical models that attempt to describe physics beyond the standard model in regimes where quantum mechanics, special relativity, and general relativity all play crucial roles simultaneously. As we continue our journey tonight through the deepest mysteries of matter and space-time, we find ourselves at the boundaries of human knowledge, where the very fabric of reality may transform in ways that our current understanding of physics can barely begin to imagine. Yet these transformations determine the fate of the most extreme objects in our universe. The death of a neutron star begins not with internal failure but with external forces that slowly push these stellar remnants beyond their quantum mechanical limits, creating scenarios where the delicate balance between degeneracy pressure and gravity finally tips toward inevitable collapse in ways that can be surprisingly gentle yet ultimately catastrophic. The most common trigger involves mass accretion from a companion star in a binary system, where matter stripped from a normal stellar partner spirals inward through an accretion disk, heating to millions of degrees and eventually settling onto the neutron star's surface with the patient persistence of cosmic rain. Over millions or billions of years, this steady accumulation of matter adds mass grain by grain to the neutron star, each additional atom bringing the object closer to the Tolman-Oppenheimer-Volkoff limit, while the star continues to spin and pulse with clockwork regularity, unaware of its approaching doom. Theoretical calculations performed at institutions like Princeton University and the California Institute of Technology show that even relatively small accretion rates of a few billionths of a solar mass per year can eventually drive a neutron star past the critical threshold, though the timescales involved often exceed the current age of the universe. A far more dramatic triggering mechanism occurs during neutron star mergers, where two of these dense objects spiral together under the influence of gravitational wave radiation, losing energy and orbital momentum until they collide in a cataclysmic event that can create a combined mass well above what either individual star could have supported alone. The merger process itself unfolds over approximately 100 seconds of detectable gravitational wave emission, with the frequency of the waves climbing from tens of hertz to thousands as the neutron stars draw closer together, their surfaces beginning to deform under mutual tidal forces that stretch and squeeze the stellar matter in ways that would destroy any ordinary material. NASA's Laser Interferometer Gravitational Wave Observatory has detected several such mergers, most notably GW 8177, which provided the first direct observation of the moment when a neutron star merger created a mass that exceeded the maximum sustainable limit and collapsed to form a black hole within seconds of the collision. Another subtle but important triggering mechanism involves the gradual loss of rotational support that can occur as neutron stars age and their spin rates decrease due to electromagnetic braking from their powerful magnetic fields. Young neutron stars often rotate hundreds of times per second, and this rapid rotation provides additional centrifugal support against gravitational collapse, allowing some objects to exist stably at masses that would be unstable for non-rotating configurations. The European Space Agency's pulsar timing programs have documented how these spin rates decrease over astronomical timescales, and for neutron stars with masses very close to the stability limit, the loss of rotational support over millions of years could eventually trigger collapse, even without any external mass addition. Temperature effects also play a crucial role in newly formed neutron stars, where the intense heat generated during the supernova explosion that created them can provide additional thermal pressure that supplements quantum degeneracy pressure during the first few years after formation. As these objects cool through neutrino emission and surface radiation, the loss of thermal support might push neutron stars that formed right at the edge of stability over the critical threshold for collapse. Advanced computer simulations conducted at research centers worldwide show that the cooling process occurs rapidly by astronomical standards, with neutron star core temperatures dropping from billions to millions of degrees within the first century after formation, potentially triggering delayed collapse in objects that initially appeared stable. The exact moment when mass exceeds the TOV limit represents a point of no return that occurs with mathematical precision, though predicting this moment requires knowledge of the nuclear equation of state that remains uncertain, despite decades of experimental and theoretical investigation. Observational programs using facilities like the Chandra X-ray Observatory continue to study neutron stars in binary systems where accretion is actively occurring, hoping to catch one of these objects in the act of approaching its maximum mass and potentially witnessing the transition from neutron star to black hole in real time. Each triggering mechanism leaves distinctive observational signatures that astronomers can use to understand which process led to a particular collapse event, with neutron star mergers producing kilonova explosions and gravitational wave bursts, while accretion-induced collapse might generate different patterns of electromagnetic radiation. As we explore these triggering mechanisms tonight, we begin to see how the universe provides multiple pathways toward the same inevitable destination, where quantum mechanical resistance finally meets its match against the relentless mathematics of general relativity, creating moments that represent some of the most dramatic phase transitions possible in the natural world. The final collapse of a neutron star unfolds with breathtaking speed across a timeline measured in milliseconds, a cosmic drama where the fate of an object containing more mass than the Sun is decided in less time than it takes for sound to travel across a single city block. In the first 10 milliseconds after the critical mass threshold is exceeded, the neutron star's core density skyrockets past the point where quantum degeneracy pressure can provide adequate support, triggering a cascade of events that occurs too rapidly for any information to reach the star's surface and warn of the impending catastrophe. During this initial phase, the core region experiences what physicists call dynamic instability, where the equilibrium between inward gravitational pull and outward quantum pressure becomes unstable to even the smallest perturbations, causing the central density to increase exponentially as matter falls inward at velocities approaching significant fractions of the speed of light. Advanced computer simulations performed at institutions like the Max Planck Institute for the Gravitational Physics show that this core collapse occurs according to the freefall timescale, with the characteristic time given by the inverse square root of the density, meaning that as density increases, the collapse accelerates dramatically until physical processes occur faster than light can cross the collapsing region. Between 20 and 100 milliseconds after the onset of instability, powerful shockwaves begin to form and propagate outward through the neutron star as the core rebounds against its own incompressibility, creating pressure pulses that race through the stellar material at velocities that can exceed the local speed of sound by factors of 10 or more. The formation and behavior of these shock waves depends critically on whether the collapse proceeds in an inside-out fashion, where the core collapses first and the outer layers follow, or an outside-in scenario, where the entire star begins collapsing simultaneously, a distinction that has profound implications for the gravitational wave signals and electromagnetic radiation produced during the final moments. Current theoretical models developed by researchers at institutions like the California Institute of Technology and Princeton University suggest that most neutron star collapses follow the inside-out pattern, where the event horizon forms first at the center of the star and then expands outward like an invisible sphere of doom that eventually engulfs the entire object. The expansion of this event horizon occurs at the speed of light through the stellar material, marking the boundary beyond which no information can ever escape to the outside universe, effectively erasing all details about the internal structure and composition of the neutron star as it transforms into a black hole. Gravitational wave emission during this collapse phase provides the only direct window into these extreme physical processes, with the frequency and amplitude of the waves encoding information about how matter behaves under conditions that can never be reproduced in terrestrial laboratories. The European Space Agency's Virgo detector and its American counterparts in the LIGO collaboration have begun to develop the sensitivity needed to detect these collapse signals, which would appear as characteristic chirps lasting only a few milliseconds, but carrying information about fundamental physics in regimes where quantum mechanics and general relativity intersect. The gravitational wave signature of neutron star collapse differs dramatically from the inspiral signals produced by binary mergers, showing a rapid increase in frequency and amplitude, followed by an abrupt cutoff when the event horizon forms and no further information can escape from the newly formed black hole. Each phase of the millisecond timeline produces distinctive patterns in the gravitational radiation, with the initial core collapse generating high-frequency waves that encode details about the nuclear equation of state, while the shock wave propagation creates lower-frequency signals that reveal information about the neutron star's structure and composition in its final moments. NASA's theoretical astrophysics programs continue to refine our understanding of this timeline through sophisticated computer models that solve Einstein's field equations coupled with the equations of relativistic hydrodynamics, creating the most detailed predictions possible for what gravitational wave detectors might observe during these extreme events. The challenge for observers lies in distinguishing genuine collapse signals from the noise that affects all sensitive gravitational wave measurements, requiring advanced data analysis techniques that can extract millisecond duration signals from instrumental backgrounds that often exceed the expected signal strength by large factors. As we follow this cosmic countdown tonight, we witness how the universe's most extreme objects can transition from stable configurations that have existed for billions of years to black holes in less time than it takes for a human heartbeat, demonstrating the dramatic non-linear behavior that emerges when physical systems are pushed beyond their fundamental limits and mathematical singularities transform from abstract concepts into observable cosmic phenomena. In the final microseconds before a neutron star transforms into a black hole, the stellar surface undergoes violent convulsions that would make the most powerful earthquakes seem gentle by comparison, as tidal forces from the collapsing core stretch and squeeze the outer layers with such intensity that the crystalline crust begins to crack and shatter in events astronomers call starquakes. These surface fractures release more energy in a single moment than the Sun produces in thousands of years, sending seismic waves racing around the neutron star at velocities approaching the speed of light, while the underlying magnetic field structure becomes twisted and amplified beyond anything previously imagined in the natural universe. The magnetic field strength, already trillions of times more powerful than Earth's field in a typical neutron star, undergoes catastrophic amplification during these final microseconds as the collapsing matter drags magnetic field lines inward and compresses them to intensities reaching 10 to the 15th Tesla, strong enough to disrupt the structure of atoms themselves if any normal matter existed in such an environment. Recent simulations performed by researchers at institutions like the California Institute of Technology and the Max Planck Institute for Gravitational Physics reveal that this magnetic field amplification occurs through a process called flux freezing, where the magnetic field lines become locked to the stellar plasma and are compressed along with the matter, creating field strengths that approach the theoretical limits imposed by quantum electrodynamics. As the surface cracking reaches its crescendo, powerful jets of matter begin to stream away from the neutron star's magnetic poles, accelerated to velocities exceeding 90% of the speed of light by magnetic forces that dwarf any other acceleration mechanism known in astrophysics. These jets represent the neutron star's final desperate attempt to shed mass and avoid complete gravitational collapse, carrying away small but significant amounts of matter enriched with heavy elements forged in the extreme nuclear reactions occurring within the collapsing core. The European Space Agency's gamma-ray observatories have detected similar jets from other astrophysical phenomena, and theoretical models suggest that neutron star collapse jets might produce brief but intensely bright flashes of gamma radiation that could be visible across billions of light-years if properly aligned with Earth-based detectors. Electromagnetic radiation from the neutron star's surface reaches peak intensity during these final microseconds, as the compressed matter radiates energy across the entire spectrum from radio waves to gamma rays, creating a brilliant farewell burst that astronomers call the last light before the event horizon forms and cuts off all communication between the collapsed object and the outside universe. Advanced computer models developed by NASA's theoretical astrophysics programs show that this electromagnetic signature carries encoded information about the neutron star's final moments, including details about its magnetic field structure, surface composition, and the exotic nuclear reactions occurring as matter density soars beyond anything that exists elsewhere in the present-day cosmos. The formation of the event horizon represents the ultimate boundary beyond which classical physics loses all meaning as space-time curvature becomes infinite and the familiar concepts of space and time break down completely, leaving behind only the gravitational field that defines a black hole. The expanding event horizon moves outward from the neutron star's center at the speed of light, engulfing first the core where the collapse began, then the intermediate layers where exotic matter transitions might be occurring, and finally the surface where electromagnetic radiation makes its last escape into the surrounding space. Gravitational wave detectors like LIGO and Virgo provide the only means of observing this final transition, as the characteristic frequency sweep of neutron star collapse suddenly cuts off when the event horizon forms, and no further gravitational radiation can escape from the newly formed black hole. The abrupt termination of both electromagnetic and gravitational wave signals marks the precise moment when a neutron star ceases to exist as a physical object and becomes instead a region of curved spacetime where matter has collapsed to infinite density according to the predictions of general relativity. Current observational campaigns, coordinated by international teams of astronomers, use networks of telescopes spanning the electromagnetic spectrum to search for the distinctive signatures of neutron star collapse, hoping to catch one of these events in progress and witness the exact moment when quantum mechanics finally surrenders to gravity's ultimate victory. As this cosmic drama reaches its inevitable conclusion tonight, we observe how the universe's most extreme objects can transition from complex physical systems governed by quantum mechanics to simple geometric features of curved spacetime in less time than it takes light to cross the diameter of a proton, demonstrating the profound unity underlying apparently different branches of theoretical physics and revealing the elegant mathematical structure that governs even the most violent phenomena in the cosmos. The exact moment when reality breaks occurs not gradually but instantaneously, when the neutron star's gravitational radius, calculated from its mass using Einstein's field equations, equals its physical radius, creating a mathematical boundary in spacetime beyond which the familiar laws of physics cease to have meaning and causality itself becomes redefined by the geometry of curved space and time. This critical radius, known as the Schwarzschild radius after Karl Schwarzschild, who first solved Einstein's equations for spherically symmetric masses, represents the distance from the center, where the escape velocity equals the speed of light, making it impossible for any signal, particle, or information to ever reach the outside universe once this boundary forms around the collapsing neutron star. The mathematics governing this transition reveals a profound truth about the nature of spacetime itself, as the curvature tensor that describes how mass distorts the geometry of the universe approaches infinite values at the center of the collapsed object, creating what physicists call a singularity, where the smooth fabric of spacetime tears apart and our current theories lose all predictive power. At the precise instant when the neutron star's surface shrinks to match its Schwarzschild radius, an event horizon forms like an invisible sphere that marks the absolute boundary between the knowable and unknowable regions of the universe, beyond which no information can ever escape to tell us what happens to the matter that continues falling inwards toward the central singularity. The formation of this event horizon occurs with mathematical precision at the moment when the neutron star's density reaches approximately 2 times 10 to the 15th grams per cubic centimeter, though this exact value depends on the still uncertain equation of state governing matter at these extreme densities that exceed anything achievable in terrestrial laboratories. Researchers at institutions like the California Institute of Technology and Princeton University have calculated that the transition from neutron star to black hole happens so rapidly that it occurs in less than the light-crossing time of the original object, meaning that different parts of the neutron star cannot communicate with each other during the collapse process, making the formation of the event horizon inevitable once the critical density threshold is exceeded. The time dilation effects predicted by general relativity create one of the most paradoxical aspects of black hole formation. As an outside observer watching the collapse would see the neutron star's surface approach the Schwarzschild radius ever more slowly, with the final moments before event horizon formation stretched out over infinite time according to the distant observer's clocks. This temporal distortion means that from our perspective here on Earth, the collapsing neutron star appears to freeze at the moment of black hole formation, its surface red-shifted to invisibility, but never quite reaching the point where the event horizon forms, even though from the perspective of matter falling with the collapse. The transition occurs in finite proper time, measured by clocks moving with the stellar material. The information paradox emerges as one of the most profound mysteries in modern physics, questioning what happens to all the detailed information about the neutron star's structure, magnetic field, rotation, and composition when this data becomes trapped behind an event horizon where it can never be retrieved by any conceivable future observation or measurement. Stephen Hawking's work on black hole thermodynamics suggests that black holes should eventually evaporate through quantum mechanical processes, but this Hawking radiation appears to carry no information about what fell into the black hole originally, creating an apparent violation of quantum mechanics which demands that information must be conserved in all physical processes. Current research programs at institutions like the European Organisation for Nuclear Research and the Massachusetts Institute of Technology attempt to resolve this paradox through various theoretical approaches, including holographic duality, which suggests that all information about the black hole interior might be encoded on its surface, and quantum error correction schemes that could preserve information through the black hole formation and evaporation process. The practical implications of event horizon formation extend beyond theoretical considerations, as the moment when this boundary appears around a collapsed neutron star marks the instant when gravitational wave emission ceases abruptly, providing observational astronomers with a characteristic signature that could be detected by advanced interferometers like LIGO and Virgo if they achieve sufficient sensitivity to observe individual neutron star collapse events. As we contemplate this moment when reality breaks tonight, we encounter the profound truth that the universe contains boundaries beyond which human knowledge cannot penetrate, regions where the mathematical descriptions that work so successfully in describing everyday phenomena become meaningless, and where the very concepts of space and time as we understand them dissolve into something far more mysterious and fundamental that lies at the heart of existence itself. The speed at which a neutron star collapses to form a black hole follows the inexorable mathematics of freefall under its own gravity, with the characteristic timescale given by the elegant formula T equals the square root of r cubed divided by 2gm, where r represents the neutron star's radius, g is Newton's gravitational constant, and m is the stellar mass, yielding a collapse time of approximately 1 millisecond for a typical neutron star. This remarkably brief duration means that the entire transformation from a stable stellar remnant that has existed for billions of years to a black hole occurs faster than the blink of an eye, faster than sound can travel through air, faster than most chemical reactions can proceed, demonstrating how dramatically nonlinear behavior emerges when physical systems cross critical thresholds and mathematical singularities transform from abstract concepts into cosmic reality. The comparison between the collapse timescale and the light-crossing time of the neutron star reveals another layer of relativistic complexity, as light requires approximately 0.07 milliseconds to travel from one side of a typical neutron star to the other, meaning that during the collapse process, different regions of the star cannot communicate with each other or coordinate their behavior in any way. This breakdown of causal connection ensures that once the collapse begins, no physical mechanism can halt the process or restore stability to the neutron star, as information about conditions in one part of the star cannot reach other regions quickly enough to trigger any kind of coordinated response to the gravitational instability. Advanced computer simulations performed at research institutions like the Max Planck Institute for Gravitational Physics show that relativistic effects become increasingly important during the final moments of collapse, as matter falls inward at velocities approaching significant fractions of the speed of light, while space-time curvature grows so extreme that the familiar Newtonian description of gravity breaks down completely. The formation of a photon sphere at precisely 1.5 times the Schwarzschild radius represents one of the most exotic phenomena occurring during these final moments, creating a region where light rays can orbit the collapsing mass in unstable circular paths that exist for only brief instants before either escaping to infinity or falling into the forming black hole. These circular photon orbits mark the boundary between light rays that can still escape the gravitational field and those that are doomed to fall inward, creating a mathematical surface that shrinks rapidly as the neutron star approaches its Schwarzschild radius, and the event horizon prepares to form around the collapsed matter. Theoretical calculations performed by researchers at institutions like the California Institute of Technology and Princeton University reveal that the photon sphere's existence during neutron star collapse could produce distinctive signatures in the electromagnetic radiation emitted during these final moments, as light rays following these unstable orbits would be highly redshifted and focused into narrow beams that might be detectable by sensitive astronomical instruments. The exact moment when reality gives up occurs at the precise instant when the neutron star's surface reaches its Schwarzschild radius, creating an event horizon beyond which the concepts of space and time as we understand them lose their meaning, and the mathematics describing physical processes develop singularities that cannot be resolved within our current theoretical framework. This moment represents a fundamental boundary in nature, where quantum mechanics, special relativity, and general relativity all converge to create conditions that push the limits of human understanding and reveal the inadequacy of our present theories to describe the most extreme states of matter and space-time curvature possible in the universe. NASA's theoretical astrophysics programs continue to study these collapse dynamics using sophisticated numerical relativity coders that solve Einstein's field equations on supercomputers capable of tracking the evolution of space-time geometry and matter distribution through the final microseconds before black hole formation. The gravitational wave emission during these final moments carries encoded information about the collapse dynamics and could potentially be detected by next-generation interferometers if they achieve sufficient sensitivity to observe the characteristic frequency evolution and abrupt cutoff that occurs when the event horizon forms and gravitational radiation can no longer escape from the newly formed black hole. European Space Agency missions planned for the coming decades will attempt to observe the electromagnetic counterparts of neutron star collapse events, searching for the distinctive signatures of photon sphere formation and the final burst of radiation that escapes just before the event horizon engulfs the stellar surface and cuts off all communication with the outside universe. As we witness this cosmic countdown tonight, we observe how the universe's most fundamental forces and most extreme objects can transition from complex physical systems governed by well-understood laws to mathematical abstractions that challenge the very foundations of our scientific worldview, demonstrating that nature contains processes so extreme that they push beyond the boundaries of current knowledge and into realms where new physics must eventually be discovered. Beyond the event horizon of a newly formed black hole lies a region forever hidden from scientific investigation, where the interior solutions to Einstein's field equations become mathematically undefined and our most successful theories of gravity and quantum mechanics reach fundamental limits that may require entirely new physics to transcend. The breakdown of general relativity occurs not gradually but catastrophically at the central singularity where the curvature of space-time approaches infinite values, creating conditions where the smooth geometric description of gravity that works so successfully throughout the rest of the universe loses all predictive power and mathematical meaning. At this point of infinite density and zero volume, the very concepts of space and time that form the foundation of our physical understanding cease to exist in any recognizable form, replaced by mathematical singularities that signal the complete failure of classical physics to describe what happens to matter and energy under the most extreme conditions possible in nature. The approach to these singular conditions reveals the fundamental incompatibility between general relativity and quantum mechanics, two theories that work perfectly in their respective domains but produce contradictory predictions when applied simultaneously to the extreme environment near the center of a collapsed neutron star. Quantum gravity effects become important when the curvature of spacetime reaches the Planck scale, where distances shrink to 10 to the minus 35 meters and times compress to 10 to the minus 43 seconds, creating a regime where the smooth spacetime geometry assumed by general relativity gives way to a quantum foam of virtual particles and fluctuating geometry that no current theory can adequately describe. Research programs at institutions like the California Institute of Technology and Princeton University attempt to develop quantum theories of gravity through approaches like string theory and loop quantum gravity, but these efforts remain incomplete and cannot yet provide definitive answers about what happens inside black holes or at the moment of gravitational collapse. The information that disappears behind the event horizon represents one of the deepest mysteries in modern physics, as all details about the neutron star's internal structure, magnetic field configuration, rotational state, and nuclear composition become permanently inaccessible to any future observational measurement once the black hole forms. This information paradox challenges fundamental principles of quantum mechanics, which demand that information about physical systems must be conserved in all processes, yet the formation of an event horizon appears to create a permanent barrier that prevents this information from ever being retrieved by observers in the outside universe. Stephen Hawking's discovery that black holes should emit thermal radiation through quantum mechanical processes near the event horizon suggests that black holes eventually evaporate completely, but this Hawking radiation appears to carry no information about what fell into the black hole originally, creating an apparent violation of quantum unitarity that has puzzled physicists for decades. Recent theoretical work by researchers at institutions like the Massachusetts Institute of Technology and the European Organization for Nuclear Research explores possible resolutions to this paradox through holographic principles that might encode all interior information on the black hole's surface, or quantum error correction mechanisms that could preserve information through the collapse and evaporation process. The moment when classical physics ends represents a fundamental boundary in human knowledge beyond which our current scientific methods cannot penetrate, not because of technological limitations, but because the very framework of space and time that underlies our theories breaks down completely. This breakdown occurs precisely at the point where quantum effects and gravitational effects become equally important, creating conditions that require a unified theory of quantum gravity that remains one of the greatest unsolved problems in theoretical physics. The European Space Agency's future missions to study gravitational waves and electromagnetic radiation from extreme astrophysical events may provide indirect clues about physics near black hole formation, but the interior of the event horizon will likely remain forever beyond direct scientific investigation. Advanced computer simulations using numerical relativity can track the collapse process up to the moment of event horizon formation, but they cannot follow the evolution of matter and spacetime beyond this point because the mathematical equations lose their physical meaning and develop singularities that cannot be resolved within our current theoretical framework. The philosophical implications of this fundamental limit extend beyond physics to questions about the nature of reality itself and whether the universe contains aspects that are inherently unknowable rather than merely difficult to observe with current technology. As we contemplate these ultimate boundaries tonight, we encounter the humbling truth that the cosmos contains regions where human reason and scientific method reach their absolute limits, where the mathematical descriptions that successfully explain everything from atomic behavior to galactic dynamics simply cease to apply, leaving us with profound questions about the nature of existence that may require revolutionary advances in our understanding of space, time, and matter to address. In this confrontation with the unknowable, we find both the limits of current knowledge and perhaps the greatest challenge facing future generations of scientists who must somehow bridge the gap between quantum mechanics and gravity to reveal what lies hidden behind the event horizons that mark the boundaries of the observable universe. The cosmic surrender of neutron stars to gravity's ultimate victory leaves behind observable fingerprints in the fabric of space-time itself, creating gravitational waves that carry encoded information about the exact moment when quantum mechanics finally admits defeat and matter crosses the threshold from which no return is possible. These ripples in spacetime follow a characteristic pattern called a chirp, where the frequency of gravitational waves increases steadily as two neutron stars spiral toward each other, their orbital separation decreasing and their mutual gravitational attraction growing stronger until the final merger and collapse occur within milliseconds of each other. The most famous example of this cosmic death song was detected on August 17, 2017, when the Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo recorded the signal designated G0817, a gravitational wave event that lasted approximately 100 seconds and exhibited the unmistakable frequency evolution expected from two neutron stars with masses of 1.1 and 1.6 times that of our Sun, spiraling inexorably toward their mutual destruction. During the inspiral phase of this merger, the gravitational wave frequency climbed from roughly 35 Hz to over 250 Hz as the neutron stars drew closer together, their surfaces beginning to deform under mutual tidal forces that stretched and squeezed the stellar matter in ways that would destroy any ordinary material, while the amplitude of the gravitational waves grew exponentially as the orbital energy was converted into ripples propagating outward at the speed of light. Advanced data analysis techniques developed by researchers at institutions like the Massachusetts Institute of Technology and the California Institute of Technology can extract detailed information about neutron star properties from these gravitational wave signatures, including masses, radii, tidal deformabilities, and the equation of state-governing matter at nuclear densities that cannot be studied in any terrestrial laboratory. The sudden cutoff of gravitational wave emission provides the most dramatic signature of neutron star collapse to a black hole, as the moment when the event horizon forms around the merged object marks the instant when no further gravitational radiation can escape to reach detectors on Earth or anywhere else in the universe. This abrupt termination of the gravitational wave signal occurs precisely when the combined mass of the neutron stars exceeds the Tolman-Oppenheimer-Volkoff limit, creating a distinctive observational signature that allows astronomers to measure the maximum mass that neutron star matter can support against gravitational collapse. Post-merger gravitational wave signatures, if they exist at all, would carry information about the internal structure and dynamics of the newly formed black hole, but current gravitational wave detectors lack the sensitivity needed to observe these extremely weak signals that would be produced by the oscillations and settling of the black hole to its final equilibrium state. The European Space Agency's planned space-based gravitational wave observatory LISA will extend observations to much lower frequencies than current ground-based detectors can access, potentially revealing new aspects of black hole formation and the transition from neutron star matter to the pure spacetime geometry that characterizes these exotic objects. Each gravitational wave detection provides an independent measurement of fundamental physics under extreme conditions, allowing researchers to test general relativity in the strong field regime, where spacetime curvature reaches values billions of times larger than anything accessible to solar system experiments or particle accelerator studies. The precision of modern gravitational wave astronomy has reached the point where scientists can distinguish between different theoretical models of neutron star matter by comparing predicted gravitational wave signatures with observed data, constraining the nuclear equation of state and improving our understanding of how matter behaves at densities exceeding those found in atomic nuclei. Future upgrades to LIGO and Virgo will increase their sensitivity by factors of 10 or more, enabling the detection of neutron star mergers at cosmological distances and providing large samples of these events for statistical studies of stellar collapse and black hole formation. The gravitational wave signals from neutron star collapse also carry information about the speed of gravity itself, as the near-simultaneous arrival of gravitational waves and electromagnetic radiation from GW 70817 confirm that gravitational disturbances propagate at exactly the speed of light as predicted by Einstein's theory, ruling out many alternative theories of gravity that had been proposed to explain cosmological observations. As we listen to these cosmic melodies tonight, we realize that gravitational wave astronomy has opened an entirely new window onto the universe's most extreme phenomena, allowing us to eavesdrop on the final conversations between neutron stars before they surrender to gravity's inexorable pull and transform from complex quantum systems into the elegant simplicity of curved spacetime that defines a black hole. The final electromagnetic death cry of merging neutron stars manifests as one of the most powerful explosions in the universe, a short gamma-ray burst lasting approximately 2 seconds that releases more energy than our Sun will produce over its entire 10 billion year lifetime, marking the exact moment when neutron star matter surrenders to gravitational collapse and transforms into something far more mysterious and profound. These gamma-ray bursts have puzzled astronomers since their discovery in the 1960s by military satellites designed to monitor nuclear weapons testing, but the simultaneous detection of gravitational waves and gamma rays from GW 170817 finally confirmed the long-suspected connection between neutron star mergers and these cosmic explosions that can be seen across billions of light-years of space. The gamma rays themselves arise from ultra-relativistic jets of matter launched from the polar regions of the collapsing neutron stars, accelerated to velocities exceeding 99.9% of the speed of light by magnetic fields that reach strengths trillions of times more powerful than anything that exists on Earth, creating conditions where ordinary matter behaves according to the strange rules of special relativity. Following the initial gamma-ray flash, X-ray and optical afterglows continue to shine for days or weeks as the high-speed jets interact with the surrounding interstellar medium, heating the sparse gas and dust to temperatures of millions of degrees and creating expanding shock waves that produce electromagnetic radiation across the entire spectrum, from radio waves to high-energy gamma rays. The European Space Agency's Integral Observatory and NASA's Fermi Gamma Ray Space Telescope detected the gamma ray burst from G0817 just 1.7 seconds after the gravitational wave signal arrived at Earth, a delay that provides crucial information about the physics of black hole formation and the mechanisms that launch the relativistic jets responsible for the electromagnetic emission. This brief delay suggests that the gamma ray production occurs after the initial merger and gravitational wave emission, possibly triggered by the formation of an accretion disk around the newly formed black hole, or by magnetic field reconnection events that occur as the neutron, star magnetic fields become twisted and amplified during the final moments before collapse. Perhaps the most spectacular electromagnetic signature of neutron star mergers comes from kilonovae, optical transients that shine thousands of times brighter than ordinary stellar explosions and display distinctive spectral features that reveal the presence of heavy elements forged in the extreme nuclear reactions that occur when neutron-rich matter is ejected during the merger process. The kilonova associated with GW-170817, designated AT 2017 GFO, was discovered by optical telescopes within hours of the gravitational wave detection, and provided the first direct observational evidence that neutron star mergers are responsible for producing approximately half of the elements heavier than iron in the universe, including gold, platinum, and uranium that cannot be created in ordinary stellar nucleosynthesis. The evolution of kilonova light curves follows a characteristic pattern where the initial blue emission from lighter R process elements gives way to redder colours as heavier lanthanide elements begin to dominate the opacity, creating a distinctive observational signature that allows astronomers to identify these events and study the nuclear physics occurring in environments that cannot be replicated in any terrestrial laboratory. Radio emissions from neutron star mergers appear days to weeks after the initial explosion as the relativistic jets begin to decelerate and interact with the surrounding medium, producing synchrotron radiation. From electrons accelerated to extreme energies by magnetic fields and shockwaves that continue to expand to long after the initial burst of gamma rays has faded away. The Very Large Array in New Mexico and similar radio observatories around the world have tracked the radio afterglow from GW-170817 for months, providing detailed information about the structure and evolution of the relativistic jets and the density of matter in the space surrounding the merger site. Advanced computer simulations performed at research institutions worldwide show that the delay between gravitational waves and electromagnetic radiation provides crucial constraints on the physics of neutron star mergers, including the mass of the resulting black hole, the amount of matter ejected during the collision, and the efficiency of converting gravitational binding energy into kinetic energy of the relativistic jets. The multi-messenger astronomy approach pioneered by the GW-170817 detection represents a revolution in our ability to study extreme astrophysical phenomena, combining gravitational wave observations with electromagnetic detections across the entire spectrum to create the most complete picture possible of what happens when neutron stars merge and surrender to gravity's ultimate authority. Future space-based observatories will extend these multi-messenger capabilities to even greater distances and sensitivities, potentially detecting hundreds of neutron star mergers per year and providing unprecedented statistical samples for studying the transition from neutron star matter to black holes under the most extreme conditions accessible to astronomical observation. Gravitational waves from merging neutron stars carry within their subtle frequency modulations and amplitude variations. A complete autopsy report of stellar death, encoding information about masses, radii, internal structure, and the exotic matter physics that governs these objects in ways that no electromagnetic observation could ever achieve. The gravitational wave signal acts like a cosmic stethoscope, allowing astronomers to listen to the final heartbeat of neutron stars and extract detailed measurements of properties that would otherwise remain forever hidden beneath impenetrable surfaces where matter exists in states more exotic than anything found elsewhere in the present universe. During the final moments before merger, tidal forces between the neutron stars cause measurable deformations that leave distinctive signatures in the gravitational wave frequency evolution, with stiffer equations of state producing smaller tidal bulges and different patterns of frequency modulation that can be distinguished by advanced data analysis, techniques developed at institutions like the Massachusetts Institute of Technology and the California Institute of Technology. These tidal measurements provide the first direct constraints on neutron star radii, a fundamental property that had eluded astronomers for decades despite intensive observations using X-ray telescopes, radio timing measurements, and other electromagnetic techniques that could measure masses with high precision but struggled to determine the physical sizes of these compact objects. The European Space Agency's gravitational wave observations, combined with electromagnetic follow-up campaigns, have begun to map the relationship between neutron star mass and radius with unprecedented accuracy, revealing how the nuclear equation of state governing matter at several times the density of atomic nuclei determines the structure and stability of these stellar remnants. Each new gravitational wave detection adds another data point to this cosmic census, gradually building up statistical samples that allow researchers to distinguish between different theoretical models of nuclear physics and constrain the properties of matter under conditions that cannot be reproduced in any conceivable terrestrial experiment. The maximum observed masses from gravitational wave events provide crucial constraints on the Tolman-Oppenheimer-Volkoff limit, with the detection of neutron star mergers that produce black holes immediately after collision, indicating that the combined mass exceeded the maximum that neutron degeneracy pressure could support under any reasonable equation of state. Advanced gravitational wave detectors planned for the next decade will increase sensitivity by factors of 10 or more, enabling the detection of neutron star mergers out to cosmological distances where hundreds or thousands of these events could be observed annually, providing unprecedented statistical power for studying the physics of dense matter and the transition from neutron stars to black holes. The precision of future gravitational wave measurements will reach the point where individual neutron star radii can be determined to within a few percent, allowing direct tests of theoretical predictions about exotic matter phases like quark deconfinement, hyperon formation, and strange matter transitions that might occur in the cores of the most massive neutron stars. NASA's theoretical astrophysics programs continue to develop sophisticated waveform models that incorporate the latest understanding of nuclear physics and general relativity, creating templates that can extract maximum information from gravitational wave observations and distinguish subtle differences between various equations of state that predict similar but not identical observable signatures. The standard siren method represents one of the most exciting applications of neutron star merger observations, using the gravitational wave signal to determine the distance to the merger independent of any electromagnetic observations, then combining this distance measurement with the redshift determined from optical spectroscopy of the host galaxy to provide a direct measurement of the Hubble constant that describes the expansion rate of the universe. This cosmological application of gravitational wave astronomy offers a completely independent check on the distance scale measurements derived from supernovae and other standard candles, potentially resolving the current tension between different methods of measuring cosmic expansion that has puzzled cosmologists for the past several years. Future space-based gravitational wave observatories like the European Space Agency's LISA mission will extend these measurements to much longer wavelengths and greater distances, potentially detecting neutron star mergers throughout the observable universe and providing thousands of standard siren measurements for precision cosmology studies. The combination of gravitational wave observations with electromagnetic counterparts creates a new form of precision in astrophysics where the properties of individual neutron stars can be measured with accuracies approaching those achieved in laboratory physics experiments, despite the fact that these objects contain more mass than the Sun compressed into volumes smaller than terrestrial cities. As we continue to develop this cosmic forensic science tonight, we realize that gravitational waves have opened an entirely new channel for studying the fundamental physics of matter and space-time under the most extreme conditions accessible to scientific investigation, allowing us to probe the very limits where quantum mechanics and general relativity intersect to determine the ultimate fate of stellar matter in our universe. In the final moments before neutron stars surrender to gravitational collapse, the extreme conditions of density, temperature, and neutron flux create cosmic foundries where the universe forges its heaviest and rarest elements through a process called rapid neutron capture nucleosynthesis that occurs nowhere else in the present cosmos with such extraordinary efficiency and scope. The neutron-rich environment created during the merger and collapse provides the perfect conditions for building elements heavier than iron through the R process, where atomic nuclei capture neutrons much faster than they can decay radioactively, allowing the construction of extremely neutron-heavy isotopes that subsequently decay into stable, heavy elements over timescales ranging from seconds to millions of years. During the collision and tidal disruption of neutron star surfaces, matter with neutron-to-proton ratios exceeding 100 to 1 gets ejected into space at velocities approaching 10% of the speed of light, carrying neutron densities that dwarf those found in the cores of the heaviest atomic nuclei, and creating conditions where rapid neutron capture can build atomic masses up to and beyond uranium in just a few seconds of intense nuclear reactions. The gold in wedding rings, the platinum in catalytic converters, the uranium in nuclear reactors, and dozens of other heavy elements that play crucial roles in modern technology and biological processes owe their existence to these catastrophic stellar deaths that occur perhaps once per century in a typical galaxy like our own Milky Way. Theoretical calculations performed by researchers at institutions like the California Institute of Technology and Oak Ridge National Laboratory show that a single neutron star merger can produce several Earth masses worth of heavy R-process elements, with gold production alone reaching quantities equivalent to hundreds of times the mass of our planet during the few seconds of violent nuclear processing that accompanies the final collapse. The distribution of these newly synthesized elements follows the dynamics of the kilonova explosion that accompanies neutron star mergers, with the fastest moving ejector carrying lighter R-process elements like silver and palladium, while the slower, more massive components transport the heaviest elements like gold, platinum, and actinides to distances that can exceed several light-years from the merger site. NASA's Hubble Space Telescope and ground-based observatories have detected the spectroscopic signatures of these heavy elements in the optical afterglows of kilonovae, providing direct observational confirmation that neutron star mergers are indeed the cosmic factories responsible for producing approximately half of all elements heavier than iron in the universe. The European Space Agency's future missions will extend these observations to greater distances and fainter objects, potentially tracking the chemical enrichment of galaxies through cosmic time as successive generations of neutron star mergers gradually increase the abundance of heavy elements available for incorporation into new stars, planets, and ultimately living organisms. The connection between neutron star collapse and the heavy elements in our solar system becomes clear when we consider that our Sun and its planetary system formed approximately 4.6 billion years ago from a molecular cloud that had been enriched by billions of years of stellar nucleosynthesis, including contributions from hundreds of thousands of neutron star mergers that occurred throughout the Milky Way's history. Isotopic analysis of meteorites reveals distinctive patterns in the ratios of different heavy element isotopes that match the predictions for R-process nucleosynthesis, providing forensic evidence that links the gold and platinum found on Earth directly to the violent deaths of neutron stars that occurred before our solar system even existed. The timing and frequency of neutron star mergers throughout cosmic history has determined not only the overall abundance of heavy elements in the universe, but also their distribution through space and time, with early galaxies experiencing rapid chemical evolution as massive stars lived short lives and produced neutron star binaries that merged within cosmologically brief timescales. Advanced computer simulations developed by research teams at institutions worldwide model the three-dimensional dynamics of R-process nucleosynthesis during neutron star mergers, tracking the nuclear reaction networks that build heavy elements while simultaneously following the hydrodynamic evolution of the ejected matter as it expands, cools, and eventually becomes incorporated into the interstellar medium. The recent detection of strontium in the optical spectrum of the kilonova AT 2017 GFO, associated with the gravitational wave event GW17, provided the first direct identification of a specific R-process element created during a neutron star merger, confirming theoretical predictions and establishing these events as the primary cosmic source of elements that are essential for rocky planet formation and biological processes. As we contemplate these cosmic consequences tonight, we realize that neutron star collapse represents far more than the death of the individual stellar objects, but rather a fundamental process of cosmic chemical evolution that has enriched the universe with the heavy elements necessary for complexity, technology, and life itself, connecting the most extreme physics imaginable to the everyday elements that make up our bodies, our planet, and our technological civilization. The transformation from neutron star to black hole represents one of the most dramatic births in the universe, creating stellar mass black holes with masses ranging from approximately 2.1 Sten, solar masses at the lower end, where neutron degeneracy pressure finally fails up to roughly 20 solar masses at the upper limit of what stellar collapse can produce, marking a distinct population of cosmic objects that differ fundamentally from their primordial and supermassive counterparts in both origin and observable properties. These stellar mass black holes emerge through the complete gravitational collapse of neutron star matter when quantum mechanical resistance finally surrenders to Einstein's curved spacetime, creating regions where the familiar concepts of matter and energy give way to pure geometry described by the Schwarzschild metric or its rotating Kerr extension if the original neutron star possessed significant angular momentum. The mass range accessible through stellar collapse reflects the physics of both stellar evolution and neutron star structure, with the lower bound determined by the maximum mass that neutron degeneracy pressure can support according to the Tolman-Oppenheimer-Volkoff limit, while the upper bound emerges from the initial masses of stars that can undergo core collapse without losing too much mass through stellar winds and supernova explosions. Unlike primordial black holes that might have formed from density fluctuations in the early universe with masses ranging from microscopic scales up to thousands of solar masses, stellar mass black holes carry the chemical fingerprints of nuclear fusion processes that occurred in their progenitor stars, influencing the metallicity and element abundances in the surrounding interstellar medium through their formation process. The distinction from supermassive black holes becomes clear when we consider that objects with millions to billions of solar masses found at galactic centers likely formed through completely different mechanisms involving direct collapse of massive gas clouds or growth through accretion and mergers over cosmological timescales, creating a population gap that spans several orders of magnitude in mass. Advanced gravitational wave observations by LIGO, Virgo, and future detectors are beginning to map the population statistics of stellar mass black holes with unprecedented precision, revealing details about their mass distribution, meander rates, and merger rates that provide crucial tests of stellar evolution models and neutron star physics. The European Space Agency's planned space-based gravitational wave observatory will extend these population studies to include lower mass objects and longer period binaries, potentially detecting intermediate mass black holes that might bridge the gap between stellar and supermassive populations. Population synthesis models developed by researchers at institutions like the Max Planck Institute for Astrophysics and Northwestern University predict that the Milky Way should contain approximately 100 million stellar mass black holes, most of which remain invisible unless they happen to be actively accreting matter from companion stars or participating in binary mergers that produce detectable gravitational waves. The mass gap between the heaviest observed neutron stars and the lightest confirmed black holes represents one of the most intriguing puzzles in stellar astrophysics, with very few objects detected in the range between 2.5 and 5 solar masses, where the transition from neutron star to black hole physics should occur most dramatically. Recent gravitational wave detections have begun to populate this mass gap with objects that challenge traditional classifications, including possible low-mass black holes that might have formed through neutron star mergers or exotic neutron stars that somehow exceed the conventional maximum mass limits predicted by standard equations of state. NASA's theoretical astrophysics programs continue to refine our understanding of stellar mass black hole formation through sophisticated computer simulations that track the entire process from the core collapse of massive stars through neutron star formation and eventual transition to black holes if sufficient mass is added through accretion or mergers. The birth process itself occurs with remarkable efficiency, converting virtually all of the neutron star's rest mass energy into gravitational binding energy, while preserving only angular momentum and electric charge as measurable properties of the resulting black hole, demonstrating the no-hair theorem that describes how black holes erase all information about the detailed structure and composition of their progenitor objects. Stellar mass black holes serve as natural laboratories for testing general relativity in this strong field regime where spacetime curvature reaches extreme values impossible to achieve in any terrestrial experiment, providing observational tests of Einstein's theory under conditions where quantum effects and classical gravity both play important roles in determining the behavior of matter and energy. The study of stellar mass black hole populations also provides crucial insights into the chemical evolution of galaxies, as these objects represent the ultimate endpoint of massive star evolution, and their formation rate tracks the star formation history and initial mass function of stellar populations throughout cosmic time, connecting the physics of individual stellar deaths to the large-scale structure and chemical enrichment of the universe itself. Neutron star collapse events represent the most extreme natural laboratories in the universe, providing unprecedented opportunities to test fundamental physics under conditions where general relativity, quantum mechanics, and nuclear physics all operate simultaneously at energy scales and field strengths that dwarf anything achievable in terrestrial experiments by factors of trillions or more. These cosmic laboratories allow scientists to probe general relativity in the strong field regime where space-time curvature reaches values billions of times larger than those accessible through solar system tests or particle accelerator experiments, creating environments where Einstein's theory faces its most stringent observational challenges and potential modifications or extensions become detectable through precise gravitational wave measurements. The gravitational fields near collapsing neutron stars approach the theoretical limits where classical general relativity might break down and require quantum corrections, offering unique opportunities to search for signatures of quantum gravity effects that could reveal new physics beyond our current understanding of spacetime and matter. Quantum mechanics operates on macroscopic scales during neutron star collapse in ways that have no analogy anywhere else in nature, with degeneracy pressure arising from the Pauli exclusion principle supporting stellar remnants containing more mass than the Sun against gravitational collapse, demonstrating how quantum mechanical principles that govern individual atoms and molecules can determine the fate of objects visible across interstellar distances. The nuclear physics governing matter at several times the density of atomic nuclei remains highly uncertain despite decades of experimental and theoretical investigation, making neutron star observations the primary source of information about how protons and neutrons behave under conditions that existed only briefly during the first microseconds after the Big Bang. Advanced gravitational wave detectors provide unprecedented sensitivity to the equation of state governing ultra-dense matter, with tidal effects during neutron star mergers encoding detailed information about nuclear incompressibility, phase transitions, and exotic matter, states that determine whether neutron stars can exist above certain critical masses or must collapse into black holes when quantum resistance finally fails. The European Space Agency's planned gravitational wave missions will extend these measurements to space-based platforms where isolation from terrestrial vibrations and longer baseline interferometry enable detection of gravitational waves from massive black hole mergers, neutron star in spirals at cosmological distances, and potentially even more exotic sources like cosmic string vibrations or phase transitions in the early universe. Nuclear physics under impossible conditions becomes accessible through multi-messenger observations that combine gravitational waves with electromagnetic radiation from kilonovae, gamma-ray bursts, and X-ray emissions, providing multiple independent probes of the same extreme physical processes and allowing researchers to cross-check theoretical predictions against observational data in more subtle ways that single-channel astronomy could never achieve. Future space missions like NASA's proposed Advanced Laser Interferometer Space Antenna and the European Space Agency's LISA Pathfinder successor will push gravitational wave astronomy into frequency ranges inaccessible from Earth, potentially revealing new classes of sources and enabling precision tests of fundamental physics that could detect deviations from general relativity at the level of parts per million or better. Ground-based detection improvements continue to increase the sensitivity and frequency range of gravitational wave observatories, with next-generation facilities like the Einstein Telescope in Europe and Cosmic Explorer in the United States promising to detect neutron star mergers throughout the observable universe, and provide statistical samples large enough for precision studies of nuclear physics and tests of alternative theories of gravity. The combination of gravitational wave observations with electromagnetic counterparts creates opportunities to measure fundamental constants like the speed of gravitational waves relative to light, test the equivalence principle under extreme conditions, and search for violations of Lorentz invariance that might arise from quantum gravity effects or extra-dimensional physics. Theoretical physics benefits enormously from these cosmic laboratories as they provide observational data that can distinguish between competing models of dense matter, quantum gravity, and modified theories of gravitation that make similar predictions under ordinary conditions but differ dramatically in their predictions for neutron star structure and black hole formation. The precision achievable with advanced gravitational wave interferometry approaches that of laboratory experiments in some respects, allowing measurements of neutron star tidal deformabilities to within a few percent and potentially detecting the gravitational wave, signatures of individual neutron star oscillation motors that encode information about internal structure and composition. Future improvements in detector technology, including quantum-enhanced interferometry and novel approaches like atom interferometry and optical clock networks, may eventually enable gravitational wave astronomy to test fundamental physics with precision exceeding that of any terrestrial experiment while probing energy scales and field strengths that will remain forever inaccessible to human technology. As we explore these cosmic laboratories tonight, we realize that neutron star collapse represents far more than astronomical curiosities, but rather unique natural experiments that push the boundaries of human knowledge and provide our best hope for understanding the fundamental laws that govern matter, energy, space, and time under the most extreme conditions accessible to scientific investigation. Beyond the familiar boundary between neutron stars and black holes lies a realm of exotic possibilities where ordinary nuclear matter might undergo dramatic phase transitions that completely alter our understanding of stellar collapse, creating intermediate objects called quark stars where the neutrons themselves break apart into their fundamental constituents and form states of matter that could be even more stable than atomic nuclei. The strange matter hypothesis, first proposed by theoretical physicists in the 1980s, suggests that under sufficient pressure and density, the up and down quarks that comprise normal protons and neutrons might be joined by strange quarks to create a form of matter that represents the true ground state of quantum chromodynamics, potentially more stable than any form of ordinary nuclear matter found elsewhere in the universe. If this hypothesis proves correct, neutron stars approaching the traditional mass limit might not collapse directly to black holes, but instead undergo a rapid phase transition where the neutron fluid transforms into strange quark matter, creating objects with fundamentally different properties, including potentially higher maximum masses that could exceed the Tolman-Oppenheimer-Volkoff limit, calculated for conventional neutron stars. Theoretical calculations performed at institutions like the Massachusetts Institute of Technology and CERN suggest that this phase transition might occur suddenly throughout the entire neutron star core once the critical density is reached, converting the object to a strange star with a thin crust of ordinary nuclear matter surrounding a core of deconfined quarks, in a process that could release enormous amounts of energy and produce distinctive observational signatures. The stability of strange matter depends critically on the strong nuclear force interactions between quarks at high densities, a regime where quantum chromodynamics becomes non-perturbative and requires sophisticated numerical techniques like lattice gauge theory to calculate these equation of state-governing quark matter under the extreme conditions found in stellar cores. Color superconductivity represents another exotic possibility that could emerge in dense quark matter, where quarks form Cooper pairs analogous to electrons in conventional superconductors, but bound together by the strong force rather than electromagnetic interactions, creating a state where the familiar color-charge symmetry of quantum chromodynamics becomes spontaneously broken. These color superconducting phases could dramatically alter the transport properties and equation of state of dense matter, potentially allowing quark stars to exist at masses well above the limits calculated for conventional neutron stars, while exhibiting novel electromagnetic and thermal properties that distinguish them from both neutron stars and black holes. The European Organization for Nuclear Research continues to study these exotic phases through high-energy heavy ion collisions that briefly create small volumes of quark-gluon plasma, providing experimental data about the phase diagram of quantum chromodynamics under conditions similar to those that might exist in neutron star cores. Strange matter droplets represent perhaps the most speculative possibility arising from these theoretical investigations, suggesting that if strange matter is indeed absolutely stable, small chunks of it could exist as stable objects that might survive the collapse of strange stars or be produced during phase transitions in neutron star mergers. NASA's theoretical astrophysics programs model how phase transitions to strange matter might alter the dynamics of neutron star collapse, potentially creating observable signatures in gravitational wave emissions as the equation of state changes discontinuously during the transition from nuclear matter to quark matter phases. The possibility of hybrid stars containing both conventional neutron matter in outer layers and strange quark matter in central cores introduces additional complexity to the mass-radius relationship that determines stellar stability, potentially creating multiple branches of stable configurations separated by unstable regions, where small perturbations could trigger rapid phase transitions. Advanced computer simulations incorporating the latest understanding of quantum chromodynamics suggest that the transition to strange matter might occur gradually rather than suddenly, creating mixed phases where conventional nucleons coexist with deconfined quarks over significant density ranges within neutron star cores. The observational signatures of these exotic phases remain highly uncertain, but might include distinctive cooling patterns as strange stars lose energy through novel neutrino emission processes, unusual magnetic field evolution as superconducting phases alter electromagnetic properties, or characteristic gravitational wave signatures during transitions between different stable configurations. Future gravitational wave observations may provide the most promising avenue for detecting these exotic states of matter, as the precise measurement of neutron star masses, radii and tidal deformabilities during merger events could reveal deviations from conventional nuclear matter equations of state that indicate the presence of phase transitions to quark matter or strange matter phases. As we explore these theoretical frontiers tonight, we encounter the possibility that the universe contains forms of matter more exotic than anything imagined when neutron stars were first discovered, reminding us that the transition from neutron star to black hole might involve intermediate stages governed by physics that pushes our understanding of fundamental interactions to their absolute limits. Among the most exotic alternatives to immediate black hole formation stands the magnetar, a neutron star whose magnetic field reaches strengths of 10 to the 15th Tesla, so powerful that it could theoretically provide additional pressure to support stellar matter beyond the conventional Tolman-Oppenheimer-Volkoff limit and delay gravitational collapse for millions or even billions of years, while slowly losing its magnetic energy to space. These ultra-strong magnetic fields represent the most intense concentrations of electromagnetic energy known in the universe, exceeding Earth's magnetic field by factors of a trillion and approaching theoretical limits where the fabric of spacetime itself begins to exhibit non-linear electromagnetic properties predicted by quantum electrodynamics but never observed under controlled conditions. The magnetic pressure generated by such extreme fields could supplement neutron degeneracy pressure in supporting the neutron star against gravitational collapse, potentially allowing magnetars to exist stably at masses that would cause conventional neutron stars to immediately form black holes, though the exact contribution of magnetic support to stellar stability remains uncertain due to the complex three-dimensional structure of magnetospheric fields. Theoretical calculations performed at institutions like Princeton University and the Max Planck Institute for Astrophysics show that magnetic pressure scales as the square of the field strength, meaning that the strongest magnetar fields could contribute pressures comparable to neutron degeneracy pressure in the outer layers of the neutron star where magnetic field lines are most concentrated. The origin of these extraordinary magnetic fields likely involves dynamo processes during the neutron star's formation, where the rapid collapse and differential rotation of the progenitor stellar core amplifies seed magnetic fields through magneto-hydrodynamic instabilities that can increase field strengths by factors of billions within the first few seconds after the supernova explosion. However, these magnetic fields cannot remain constant indefinitely, but must slowly decay through various physical processes, including ohmic dissipation in the neutron star crust, magnetic reconnection events that release energy in violent outbursts, and magnetospheric currents that radiate electromagnetic energy away from the star at rates determined by the field geometry and stellar rotation. The European Space Agency's X-ray observatories have detected evidence for magnetic field decay in several magnetars through long-term monitoring campaigns that reveal gradual changes in their emission properties, pulse profiles, and burst activity over timescales ranging from years to decades. As magnetic field strength decreases over geological timescales, any additional support provided by magnetic pressure would gradually diminish, potentially pushing magnetars that initially existed above the conventional neutron star mass limit toward delayed gravitational collapse when their magnetic fields finally weaken below critical thresholds. The magnetospheric evolution of these objects involves complex interactions between the neutron star's solid crust and its powerful magnetic field, leading to stress accumulation that periodically releases through catastrophic fracturing events called starquakes that can rival the energy output of solar flares while simultaneously reorganizing the magnetic field structure in ways that affect the long-term stability of the entire system. NASA's Fermi Gamma Ray Space Telescope and other high-energy observatories have detected numerous magnetar outbursts that release more energy in a fraction of a second than the Sun produces in years, providing direct evidence for the violent processes that accompany magnetic field evolution and stress release in neutron star crusts, strained beyond their elastic limits. The starquake mechanism involves the accumulation of magnetic stress in the neutron star crust, as the internal magnetic field evolves on timescales much longer than the elastic response time of the solid surface layers, eventually leading to sudden fractures that propagate through the crust at speeds approaching the speed of sound while releasing stored magnetic energy in explosive events that can be detected across interstellar distances. Computer simulations of magnetar evolution developed by research teams worldwide attempt to model the complex interplay between magnetic field decay, crustal stress accumulation, and starquake activity, predicting how these processes might affect the long-term stability of magnetars that initially exist near the maximum mass limit for neutron star matter. The delayed collapse scenario suggests that some magnetars might undergo gravitational collapse to black holes millions of years after their initial formation, triggered not by mass accretion or external perturbations, but by the gradual loss of magnetic support as their extraordinary fields slowly decay through electromagnetic radiation and particle acceleration processes. Future gravitational wave detectors may be sensitive enough to detect the characteristic, signals from delayed magnetar collapse, which would differ from conventional neutron-star merger or accretion-induced collapse, through distinctive frequency evolution patterns that encode information about magnetic field structure and decay processes operating over astrophysical timescales. As we contemplate these magnetic monsters tonight, we realize that the transition from neutron star to black hole may not always occur immediately, but could sometimes be postponed for cosmologically significant periods by electromagnetic forces that rival gravity itself in their ability to support stellar matter against the ultimate pull toward infinite density and zero volume. The rapid rotation of neutron stars provides an additional mechanism for supporting stellar matter against gravitational collapse, with centrifugal forces generated by spin rates reaching hundreds of revolutions per second, creating outward pressures that can supplement quantum degeneracy effects and allow rotating neutron stars to exist stably at masses that would cause non-rotating objects to immediately form black holes. The fastest spinning neutron stars known to astronomers are millisecond pulsars that rotate between 300 and 700 times per second, approaching the theoretical maximum spin rates beyond which even the strongest materials would be torn apart by centrifugal forces that overcome the gravitational binding holding the stellar surface together. These millisecond pulsars represent the end products of binary evolution, where mass transfer from a companion star spins up the neutron star through accretion processes that can operate over billions of years, gradually increasing the angular momentum until rotation provides significant support against gravitational compression in the equatorial regions where centrifugal effects are strongest. The maximum rotation rate for neutron stars depends critically on their equation of state and mass-radius relationship, with theoretical calculations suggesting that breakup occurs when the centripetal acceleration at the equatorial surface equals the local gravitational acceleration, typically corresponding to spin periods between 0.5 and 1.5 milliseconds depending on the stellar mass and nuclear physics governing dense matter. Research conducted at institutions like the California Institute of Technology and Cornell University shows that rotational support can increase the maximum stable mass of neutron stars by 10 to 20% above the non-rotating Tolman-Oppenheimer-Volkoff limit, potentially allowing some objects to avoid immediate collapse to black holes even when their masses exceed what static neutron star configurations could support. However, this rotational support cannot persist indefinitely because neutron stars inevitably lose angular momentum through electromagnetic radiation emitted by their powerful magnetic fields, and charged particles accelerated in their magnetospheres, causing them to spin down over timescales ranging from millions to billions of years depending on their magnetic field strength and initial rotation rate. The European Space Agency's pulsar timing programs have documented this spin-down process in hundreds of neutron stars, measuring the gradual increase in pulse periods that occurs as rotational energy is converted to electromagnetic radiation and particle acceleration, creating a population of neutron stars at various stages of magnetic braking evolution. Advanced theoretical models developed by researchers worldwide predict that neutron stars supported partially by rotation might undergo delayed collapse to black holes when their spin rates decrease below critical thresholds, where centrifugal support can no longer compensate for masses that exceed the static stability limit, creating a delayed collapse scenario that could occur millions of years after the initial neutron star formation. The spin-down process itself generates distinctive observational signatures, including the gradual increase in pulse periods measured by radio telescopes, occasional glitches where the neutron star suddenly spins up due to interactions between the solid crust and superfluid interior, and long-term changes in pulse profile shape as the magnetic field structure evolves over geological timescales. Gravitational wave emission from rapidly rotating neutron stars represents another mechanism for angular momentum loss that could accelerate the approach toward delayed collapse, particularly through R-mode oscillations that become unstable in rapidly spinning stars and convert rotational kinetic energy into gravitational radiation that carries angular momentum away from the system. The Laser Interferometer Gravitational Wave Observatory and Virgo detectors continue searching for continuous gravitational waves from spinning neutron stars, hoping to detect the characteristic frequency-doubled signals produced by asymmetric mass distributions or R-mode instabilities in the galactic neutron star population. NASA's theoretical astrophysics programs model the complex interplay between magnetic braking, gravitational wave emission, and rotational support in neutron stars approaching the mass stability limit, predicting how these processes might combine to determine the timescales for delayed collapse and the observational signatures that might herald such events. The R-mode instability mechanism represents a particularly intriguing possibility where rapidly rotating neutron stars develop oscillation patterns that grow exponentially and emit gravitational waves at frequencies twice the rotation rate, potentially spinning down massive neutron stars below their critical support thresholds within thousands of years rather than millions. Future gravitational wave observations may provide the first direct detection of rotational collapse events, where neutron stars transition from stable spinning configurations to black holes as their angular momentum decreases below critical values, producing distinctive gravitational wave signatures that encode information about both the nuclear equation of state and the dynamics of angular momentum transport in dense stellar matter. As we consider these spinning stellar remnants tonight, we encounter yet another way that neutron stars can postpone their ultimate surrender to gravity, using rotational energy stored during their violent birth to maintain temporary victory over collapse, while slowly bleeding away their angular momentum to electromagnetic fields and gravitational waves until centrifugal support finally fails and quantum mechanics admits defeat to the relentless mathematics of curved spacetime. The iron flowing through your bloodstream at this very moment carries within its atomic nucleus the memory of a neutron star's violent death, forged in the final seconds before stellar collapse, when temperatures exceeded 1 billion degrees and nuclear reactions proceeded faster than anywhere else in the present universe, creating the essential element that now enables oxygen to travel from your lungs to every cell in your body. This remarkable connection between cosmic catastrophe and human biology extends far beyond poetic metaphor, representing a direct physical lineage that links the most extreme physics imaginable to the biochemical processes that sustain consciousness, thought, and the very ability to contemplate our place in the cosmos. The calcium that provides structural strength to your bones and enables nerve signals to propagate through your brain was synthesized during the explosive death of massive stars, where shockwaves racing outward at thousands of kilometers per second triggered the nuclear reactions that built elements heavier than carbon and oxygen through the rapid fusion of lighter atomic nuclei under conditions of unimaginable violence and beauty. Every breath you take contains nitrogen atoms that were forged in stellar cores during the final moments before neutron star formation, when gravitational collapse compressed matter to densities approaching those found in atomic nuclei, while temperatures soared to levels that dwarf the interior of our sun by factors of thousands, creating the nuclear furnaces necessary to build the complex elements that form the molecular machinery of life. The gold in wedding rings and electronic devices carries an even more exotic pedigree, created not during ordinary stellar explosions but specifically during neutron star mergers, where the collision and tidal disruption of these dense objects produces neutron fluxes intense enough to drive the rapid neutron capture processes that build the heavier stable elements in the periodic table. Recent observations of kilonova explosions by NASA's Hubble Space Telescope and ground-based observatories have provided direct spectroscopic evidence that neutron star mergers produce several Earth masses worth of gold, platinum, and other precious metals during each collision, dispersing these elements through space where they'd eventually become incorporated into new generations of stars, planets, and ultimately living organisms. The phosphorus in your DNA that stores genetic information and enables the complex chemistry of cellular metabolism was created during supernova explosions that scattered these newly synthesized elements across vast volumes of interstellar space, where they mixed with hydrogen and helium from the Big Bang to form the molecular clouds that eventually collapsed to create our solar system approximately 4.6 billion years ago. This cosmic recycling process means that virtually every element in your body heavier than hydrogen has passed through at least one complete stellar life cycle, experiencing the extreme conditions of nuclear fusion, supernova explosion, neutron star formation, and possibly even neutron star mergers before becoming part of the planets and life forms that populate our corner of the universe. The European Space Agency's studies of galactic chemical evolution show that the heavy element abundances measured in our solar system match precisely the predictions for a galaxy that has experienced billions of years of stellar nucleosynthesis, including contributions from millions of neutron star mergers that gradually enriched the interstellar medium with the raw materials necessary for rocky planet formation and biological complexity. Even the trace elements essential for biological function, including cobalt in vitamin B12, molybdenum in crucial enzymes, and iodine in thyroid hormones, owe their existence to the nuclear processes that occur during the most violent stellar deaths, creating a direct connection between the physics of neutron star collapse and the biochemical pathways that enable complex life to emerge and evolve. Isotopic analysis of meteorites reveals distinctive patterns in heavy element ratios that serve as forensic evidence for specific types of stellar explosions, allowing scientists to trace the galactic history of nucleosynthesis and determine which stellar processes contributed to the chemical composition of our solar system during its formation from an ancient molecular cloud. The realization that we are literally made of collapsed star material represents more than a fascinating scientific fact, but rather a profound statement about cosmic interconnectedness, showing that the same physical laws governing neutron star collapse also govern the chemistry of life and the emergence of consciousness capable of understanding its own cosmic origins. Research conducted at institutions worldwide continues to refine our understanding of stellar nucleosynthesis and galactic chemical evolution, using observations of distant galaxies and stellar populations to map the cosmic history of element production and trace how successive generations of stellar death and rebirth have gradually transformed a universe initially composed almost entirely of hydrogen and helium into one rich enough in rich, heavy elements to support the complex chemistry necessary for planets, life, and intelligence. As we contemplate this profound connection tonight, we realize that neutron star collapse represents not just an abstract physical process occurring in distant corners of the galaxy, but rather an integral part of our own existence, linking the most extreme manifestations of gravity and quantum mechanics to the ordinary matter that forms our bodies and enables our consciousness to contemplate the very stellar deaths that made our existence possible. The future of detecting neutron star collapse will be revolutionized by next-generation gravitational wave observatories that promise sensitivity improvements of factors of 10 or more beyond current capabilities, enabling astronomers to observe these cosmic catastrophes throughout the entire observable universe and accumulate statistical samples large enough to probe the fundamental physics governing matter under the most extreme conditions accessible to scientific investigation. The European Space Agency's Laser Interferometer Space Antenna mission, scheduled for launch in the 2030s, will consist of 3 spacecraft separated by millions of kilometers, forming a gigantic gravitational wave detector in space free from terrestrial vibrations and capable of observing low-frequency gravitational waves that cannot be detected from Earth due to ground motion and atmospheric effects. This space-based observatory will complement ground-based detectors like the proposed Einstein telescope in Europe and Cosmic Explorer in the United States. Facilities that will use advanced quantum technologies including squeezed light interferometry and crystalline mirror substrates to achieve unprecedented sensitivity across frequency ranges optimized for neutron star observations. The Einstein telescope design calls for a triangular underground facility with 10-kilometer arms cooled to cryogenic temperatures and isolated from environmental disturbances, potentially capable of detecting neutron star mergers at redshifts approaching the epoch of ionization when the first stars and galaxies were forming in the early universe. These future detectors will measure the exact moment of neutron star collapse, with precision approaching microseconds, encoding information about the nuclear equation of state, quantum phase transitions, and exotic matter properties through subtle variations in gravitational wave frequency, evolution that current observatories cannot resolve with sufficient accuracy. NASA's theoretical astrophysics programs continue developing sophisticated data analysis techniques that will extract maximum information from these future observations, including machine learning algorithms trained on millions of simulated waveforms that can distinguish between different collapse scenarios and identify signatures of previously unknown physics. The combination of space-based and ground-based gravitational wave observatories will create a network spanning frequency ranges from millihertz to kilohertz, enabling continuous monitoring of neutron star systems from their early in spiral phase through merger and collapse to the final black hole formation, providing complete observational coverage of the entire process by which quantum mechanics surrenders to general relativity. Multi-messenger astronomy represents perhaps the most promising approach for understanding neutron star collapse, combining gravitational wave observations with electromagnetic detections across the entire spectrum, from radio waves to gamma rays, neutrino observations using facilities like IceCube and future detectors, and potentially even cosmic ray measurements that could reveal the highest energy particles accelerated during these extreme events. The European Southern Observatory's extremely large telescope and NASA's planned space-based observatories will provide electromagnetic follow-up capabilities with sensitivity and resolution sufficient to study kilonova explosions and gamma-ray burst afterglows at cosmological distances, revealing the detailed physics of element synthesis and energy release during neutron star death. Future neutrino observatories, including the proposed IceCube Gen 2 facility and deep-sea detectors, will search for the characteristic neutrino signatures of neutron star collapse, potentially providing unique insights into the core physics that occurs during the final moments before black hole formation, when electromagnetic radiation cannot escape but neutrinos can still carry information from the collapsing stellar interior. Advanced computational capabilities enabled by exascale supercomputers and quantum computing technologies will allow researchers to perform full three-dimensional simulations of neutron star collapse with unprecedented realism, incorporating the latest understanding of nuclear physics, magnetic field evolution, and relativistic fluid dynamics to create theoretical predictions that can be directly compared with multi-messenger observations. The fundamental physics questions that these future observations hope to address include the exact location of the boundary between neutron star and black hole phases of matter, the nature of phase transitions in ultra-dense nuclear matter, the validity of general relativity under extreme conditions, and the possible existence of exotic states like strange matter or color superconductivity that could alter the conventional picture of stellar collapse. International collaborations involving thousands of scientists from institutions around the world are already planning the data analysis strategies and theoretical frameworks needed to interpret the flood of new information that will come from these next-generation observatories, preparing to answer questions about fundamental physics that have puzzled researchers for decades. The precision achievable with these future detectors may even enable tests of quantum gravity effects near the event horizon formation, searching for subtle deviations from classical general relativity that could provide the first observational evidence for the quantum nature of spacetime itself at scales approaching the Planck length where current theories predict their own breakdown. As we look toward this observational future tonight, we anticipate a revolutionary period in our understanding of the most extreme physics in the universe, where the exact moment that neutrons give up and reality breaks will finally be captured with the precision and clarity needed to answer fundamental questions about the nature of matter, energy, space, and time under conditions that push every known physical law to its absolute limits. In the quiet contemplation of neutron star collapse, we encounter one of the universe's most profound boundaries, a place where the familiar world of matter and energy reaches its absolute limit and gives way to something far more mysterious, teaching us that even in a cosmos governed by mathematical laws, there exist moments when physics itself must admit defeat and surrender to forces beyond its current ability to describe or understand. These stellar remnants represent the last stand of ordinary matter against the pull of infinite gravity, marking the precise boundary between a universe we can measure, analyze, and comprehend through scientific methods and regions that lie forever beyond the reach of human knowledge, hidden behind event horizons where the very concepts of space and time lose their meaning. The moment when neutron degeneracy pressure finally fails after billions of years of faithful resistance carries within it a lesson about the nature of limits themselves, showing us that even the most exotic quantum forces operating at their maximum possible strength must eventually yield to mathematical inevitabilities written into the fundamental structure of reality. There exists something deeply humbling about witnessing the surrender of forces that can support matter at densities exceeding atomic nuclei, pressures that dwarf anything achievable through human technology, and magnetic fields that could disrupt the structure of atoms themselves. Yet all of this exotic physics proves insufficient when confronted with the simple mathematics of Einstein's field equations and the relentless geometry of curved space-time. This cosmic surrender resonates with our own human experience of confronting limitations, those moments when our best efforts, deepest understanding, and strongest will must acknowledge boundaries beyond which we cannot pass, teaching us that there is profound wisdom in recognizing when we have reached the edges of what is possible, rather than continuing to struggle against the inevitable. The beauty of neutron star collapse lies not in the violence of the process, but in the elegant mathematical precision with which nature has constructed these boundaries, creating transitions from the complex quantum world of matter to the simple geometric descriptions of black holes, with a clarity and definiteness that reveals the deep order underlying even the most chaotic-seeming cosmic events. In the final milliseconds before reality breaks, we witness a universe that operates according to principles more fundamental than any human emotion or desire, following laws that care nothing for our preferences, yet somehow manage to create conditions where complexity, consciousness, and the capacity for wonder can emerge from the interplay between quantum mechanics and gravity. The physics that governs these extreme events remains beautifully indifferent to human concerns, while simultaneously enabling the very existence of beings capable of contemplating their own cosmic origins, creating a paradox where the most impersonal forces in nature give rise to the deeply personal experience of consciousness trying to understand its place in the cosmos. Finding peace in the universe's ultimate mysteries requires accepting that some questions may never have answers accessible to human minds, that the regions beyond event horizons and the moments when space-time curvature becomes infinite represent not failures of scientific method, but rather natural boundaries that define the scope of what can be known while pointing toward realms that transcend ordinary understanding. The meditation on cosmic limits reveals that boundaries are not barriers to be overcome, but rather essential features that give shape and meaning to existence, just as the edges of a painting define the artwork and the limits of a musical composition create the structure within which beauty can emerge through the interplay of sound and silence. Neutron stars teach us that the universe contains both the utterly familiar, where quantum mechanics describes the behavior of particles we can study in laboratories, and the completely unknowable, where those same particles disappear into regions that might as well be located in entirely different dimensions of existence beyond the reach of any conceivable measurement or observation. The mathematical descriptions that work so successfully throughout the observable cosmos suddenly develop singularities and infinities when applied to the cores of black holes, suggesting that reality itself contains built-in limitations on what can be computed, predicted, or understood through the rational methods that have proven so powerful in every other domain of scientific investigation. In contemplating these cosmic boundaries tonight, we find ourselves in the company of the greatest mysteries that existence has to offer, standing at the edge of human knowledge, where the familiar gives way to the unknowable, where the complex yields to the simple, and where the material universe acknowledges limits that point towards something far deeper and more mysterious than anything our current understanding can encompass. There is profound peace to be found in this recognition that we are part of a universe vast enough to contain boundaries beyond which even physics cannot venture, humble enough to admit its own limitations, and elegant enough to encode those limitations in mathematical relationships that we can appreciate even if we cannot fully comprehend their ultimate implications for the nature of reality itself. Tonight, as you gaze upward, at the gentle points of light scattered across the darkness above, you are witnessing the quiet afterglow of cosmic violence that occurred billions of years ago, each star carrying within its spectrum the chemical fingerprints of neutron star collapses that forged the heavy elements now flowing through your bloodstream and forming the very neurons that enable this moment of contemplation. The light reaching your eyes from distant pulsars began its journey across the galaxy when these stellar remnants were young, spinning hundreds of times per second in their cosmic dance between quantum mechanics and gravity, their lighthouse beams sweeping through space with clockwork precision, while slowly losing energy to electromagnetic radiation and gravitational waves. In this ceaseful moment, the same physical laws that govern the violent surrender of neutron stars to black hole formation also govern the gentle processes of life itself, from the calcium-mediated nerve signals that carry thoughts through your brain to the ion-catalyzed reactions that extract energy from the food you eat, demonstrating the profound unity that connects the most extreme cosmic phenomena to the quietest biological processes. The oxygen you breathe was forged in the cores of massive stars during their final moments before neutron star formation, created when nuclear fusion reactions proceeded at rates that dwarf the energy production of our Sun by factors of millions. Yet this same oxygen now participates in the serene chemical processes that sustain consciousness and enable the capacity for wonder at our cosmic origins. There is something deeply moving about the realization that every atom in your body has participated in this cosmic recycling process, traveling from the hearts of dying stars through the cold depths of interstellar space before becoming part of the molecular clouds that collapse to form our solar system, eventually finding its way into the complex chemistry that makes possible the emergence of beings capable of understanding their own stellar heritage. The neutron stars spinning quietly in the darkness tonight will continue their patient existence for billions more years, slowly losing rotational energy while their surfaces cool from millions to thousands of degrees, their magnetic fields gradually decaying while they serve as cosmic lighthouses whose precise timing enables astronomers to test the fundamental laws of physics with unprecedented accuracy. As sleep approaches and consciousness begins to fade, we can find comfort in knowing that the same quantum mechanical principles that prevent neutron star collapse also govern the molecular processes of memory formation, the folding of proteins that maintain cellular structure, and the delicate biochemical balances that will restore your energy while you dream beneath skies filled with the remnants of stellar death and rebirth. The gravitational waves from distant neutron star mergers that occurred millions of years ago are passing through your body at this very moment, carrying information about cosmic events so energetic that they briefly outshone entire galaxies, yet these ripples in spacetime are so gentle that they stretch and compress the distance between your atoms by less than 1,000th of the width of a proton. In the morning, when you wake refreshed and ready to face another day of human experience, the same stars will continue their cosmic dance, some approaching the moment when quantum mechanics will finally surrender to gravity's pull, others beginning the long journey from neutron star to black hole that may take longer than the current age of the universe to complete. The mathematical equations that describe neutron star collapse also describe the neural networks that process thoughts and emotions, the chemical bonds that hold molecules together, and the physical forces that enable the complex patterns of matter, an energy we call life, to persist and flourish in a universe that began with nothing more than hydrogen and helium. Tonight's meditation on cosmic limits reminds us that consciousness itself represents one of the universe's most remarkable achievements, emerging from the interplay of forces that range from quantum mechanical to gravitational, creating beings capable of contemplating the very stellar processes that provided the raw materials for their existence. The peaceful rhythm of your breathing carries you towards sleep, while neutron stars continue their silent rotation in distant corners of the galaxy, their existence serving as monuments to the triumph of quantum mechanics over gravity in regimes where both forces operate at their maximum possible strength, creating cosmic laboratories that probe the deepest mysteries of matter, energy, space, and time. As you drift into dreams, carried by neural processes that depend on elements forged in stellar cores, remember that you are both observer and participant in the grand cosmic story that connects the smallest quantum effects to the largest gravitational phenomena, united by physical laws elegant enough to describe both the collapse of neutron stars and the emergence of consciousness capable of appreciating the profound beauty hidden within the mathematical structure of reality itself. Rest well tonight, knowing that the universe has conspired across billions of years and countless stellar deaths to create the conditions necessary for this moment of peaceful contemplation, when a conscious being can lie beneath ancient starlight and feel genuine gratitude for the cosmic processes that made awareness possible in the first place. Thank you, dear listener, for travelling with me through this cosmic journey to the very edge of what the universe allows. If this quiet exploration of stellar surrender brought you even a moment of wonder or peace, a gentle tap on that subscribe button would mean more to me than you might imagine. It helps keep these midnight stories alive among the stars, reaching other curious souls who find comfort in contemplating the profound mysteries that surround us. I'd love to hear where you're listening from tonight, or which part of this journey through quantum collapse touched your thoughts most deeply. Your words are like distant starlight to me, guiding these explorations forward. Until we meet again at the boundaries of the known and unknowable, rest easy, knowing that the same cosmic forces that govern neutron star death also cradle the gentle processes of sleep and dreams. May your night be filled with peaceful rest under skies that carry the memory of ancient stellar surrenders, and may you wake tomorrow with renewed wonder at the elegant mathematics that shapes our existence. Sweet dreams, fellow travellers of the cosmos.